Hey, welcome back to your favorite pre-calc class. This is section 2.3, properties of functions. There's our objectives listed there. Let's start off with our definition of a function, of an even function there. If you notice, f of negative x equals f of x is our requirement to be an even function. When I'm thinking even, you guys, I'm always thinking of the quadratic function here. Let me get my little pen here. I forgot to grab that. So always think of y equals x squared. That's what you want to think of when you think of even function. The test is f of negative x must equal f of x. Oops, that's equal f of x. Okay. So here's our f of x. I'll show you here how it works with this one. So if you test negative x in, you replace negative x for x, it's supposed to spit out, notice this is x squared. If it's truly even, it will spit out the original function, which it did. The original function was x squared. So f of negative x equals f of x. And you see that this is an even function. And you notice it is reflective about the y-axis. It's reflective about the y-axis there. See that point? And you've got this point over here. xy, you have negative xy. Whereas odd, when you see odd, you're thinking about the function f of x equals x cubed when you're thinking odd, okay? So, for instance, odd, you want to think of x cubed function. That's who you want to think of with x cubed. So you have the point like 2, 8, xy. That means you're going to have the point negative x, negative y. You'd have the point negative 2, negative 8. So here's the test. F of negative x should equal negative f of x. So, for instance, you have the point, you have f of x equals x cubed, right? Here's our original function. F of x equals x cubed. So when I plug in negative x for x, notice it spits out negative the original function. So f of negative x spits out opposite the original function f of x for it to be odd. And an odd graph is symmetric with respect to the origin. Okay. So A, is A even, odd, or neither? And you say, well, it is even. Notice if it is reflective, I have this point. Gosh, why is this thing not drawn for me? I have this point here. I've got that, if that was 3, 1, I have the point negative 3, 1. So this thing is even right here. This one, is it even? Well, no, if it was even, if I had, 1, 0, I would have negative 1, 0. So it's not even. Is it odd? Well, if I have this point 5, 4, I should have the point, if I have 5, 4 right here, 5, 4, I should have negative 5, negative 4 down here, right? If it was reflective about the origin. Or if you want to look at this point, if you got the point negative 1, 3, then I should have 1, negative 3 right down here, 1, negative 3, and it's not. So this is neither. This is neither. Okay, and this one is going to end up being odd. It's reflective about the origin there. You notice the point. What is that? 2, 4, we'll say, and you get the point negative 2, negative 4 right down there. And all those points flip around the origin. Alright, determine if it's even, odd, or neither. So if you're looking at that x squared minus 5, the first thing, if it's even, then when I plug in negative x, it'll spit out my original f of x. So let's plug in negative x. So I got negative x squared minus 5. That becomes x squared minus 5. Okay. Is this function, is this what we started with? Yes, that's our original f of x. So notice f of negative x equals f of x, thus this thing is even. Okay. So we can stop there. If it's even, it's not going to be odd or neither. Let's do the next one, x cubed minus 1. So is this, let's check if it's even first. So we plug in negative x, and we say, when I plug negative x in, is it the original function? I say, well, that's not the original. It's negative x cubed minus 1. So it's not even. Is it negative the original? Well, let me factor out a negative here. So is it negative? Is this right here? Is that g of x that we started with? No, it's x cubed plus 1, not x cubed minus 1. So it is not negative g of x either. So this is not odd. It was not even, we knew that. It's not odd either. This didn't work, right? So it's neither. In this case, that one is neither. Okay? So that's how you're going to go about those. You're just going to plug in your, there's this here. You're going to test those. You can see when you plug in negative x. Let's do this one. Let's do one more before we move on here. So we got h of x equals 5x cubed minus x. We plug in negative x. So we have 5 times negative x cubed minus a negative x. So we got negative 5x cubed plus x. And we say, was that what we started with? No, it's not the original function, so this is not even. Is it negative? Let me factor out a negative. Is it negative? Is this the original? 5x cubed minus x? It sure is, so it's negative the original. So h of negative x equals negative h of x, so this thing is odd. Okay, so that's how you'll go about those there. Alright, a function is increasing, so I think this is better seen. Those were the definitions, but I think it's better seen visually here. A function is increasing if you pick any x1, so let me pick an x1 right there, and it's less than x2. The f of x1, the y value right there, the f of x1, gosh, why isn't this thing going for me? Okay, your f of x1, the y value will be lower, less than your f of x2. So in other words, if you're increasing, you're going to be going up and to the right. If you're decreasing on a function, you should be going down and to the right. If you're constant, you should have a slope of 0. So your f of x1 will equal your f of x2. So if you're looking at a function like this, and you're naming these, first of all, let's name, where is this thing increasing? Okay, and you want to name these as open intervals. So you notice that it's increasing right from there to there. It's going up and to the right. So you take that x value from negative 4. It's an open interval. These are open intervals. You do not include the negative 4. Negative 4 is not, at that point, is not considered to be increasing. If you have more questions about why it's an open interval, that's a good calculus question. Wait till calculus. Up to this x value up here at 0. Notice it's increasing clear up until this x value right there at 0. So it's increasing on that interval. That's the only place it's going up and to the right. Where is this decreasing? Let's do this thing decreasing. Notice it's decreasing from there to there. So from negative 6 to negative 4. It's decreasing. And we're also decreasing right there. So from 3 to 6. And finally, where are we? Constant. Where are we? Constant. You see we're constant from there to there. So from 0 to an x value of 3 is where you are constant on this thing. Okay. Now let's talk about local maximums and local minimums. Your definition of a local max and local min stated right there. That just says if I if I pick an area, if I have an area, this is an open interval. So in an area, so from this x to that x, a local max will simply be the highest point there, the highest y value. So right there, if you can see that, right? Whereas a local min, again, in an open interval, from there to there, do I have a lowest point? Well, right there's our lowest point. That's our local minimum. Okay? So we're going to do some examples right here with this one. I'm going to state the local maxes and local minimums. So let's start with our local, let's do our local max first. So I say, well, do I have a local max? And again, I'm just looking for, do I have a top of a hill? Yes, you see it right here. That's the top of a little hill. So in an interval, all right, so in this interval, notice, that's the highest point, that 1, 2. So the local max is 2. It's the functional value, it's the y value there. It occurs at an x value of 2, at an x value of 1, or you can state it as an ordered pair. It occurs at 1, 2. Now, local max, do you have a local max, local min? So you bet, here's a local min. It's a bottom of a valley, right? It just happens right there. Local min, so the local min is 1, and it occurs at negative 1, 1. You also have a local min right here, if you notice, another bottom of a valley there. So the local min is 0, and it occurs at 3, 0. Alright, so now absolute max and absolute min. Now these can be on an interval, and this can be a closed interval as well. And absolute meaning the highest point. The highest point. So you notice this right here. On this interval that you're looking in, that's the highest point. So f of u is the absolute max, and it occurs at u, f of u. Okay, so absolute, local means in whatever little area that you're going to, open interval you're going to look in. Absolute means, typically speaking, on the entire domain, unless they tell you otherwise. Okay, so let's do these right here, these examples. Okay, let me move this down, get a little better picture of this one. So here we go on this one right here. Do you have a, first of all, let's talk about an absolute min. Here's your absolute min right there. That is absolutely the minimum point. So the absolute min is 1. It occurs at 0, 1. This right here is a local min. Okay, this one's the absolute min. Alright, so an absolute min, it can occur, absolute would be on a closed interval. Local mins are only on an open interval, so you cannot have a local min right here at an endpoint. Right, so this is only an absolute min. This one up here is only a local min. Now, do you have an absolute max? Yeah, that's the highest point right there. That's the absolute max. Okay, this 5, 5 is not a local max. Remember, a local max or local min cannot occur at an endpoint because they're on an open interval. Okay, let's keep moving this. Oops. Move this down here. There we go. Alright, now notice this one. You see that 3, 1 right there? I know you might think, oh, is that a local, or is that an absolute min? No, the point is not there. It's not defined. So there is no local, there is no absolute min, nor is it a local min. It is undefined. Now this one right here, though, we do have an absolute max right there. That is absolute max. Okay, but again, no local min, no absolute min on this one. Okay, let's move down to here. Absolute max, right there, there's our absolute max. And notice right here we're constant. It stays constant right through here. I can draw on it. There we go. Stays constant right through there. So that is an absolute min as well as a local min. It is 1, and it occurs, that's the y value of 1, it occurs on an interval from an x value of 1 up to an x value of 2 is where that absolute min, which is also a local min, occurs there. Okay. Alright, let's keep going. This right here would be an absolute minimum. Again, this is not, so the absolute min of 0, and it occurs at 0, 0. This is not a local min because it's at an endpoint, but it is an absolute min on this entire graph. That's the lowest point. Is there an absolute max? No, this thing just keeps going up. So there's no highest point. There's also no local max, which would be the top of a mountain. Okay, that brings us to our last one here. Notice this is not included, so there's no absolute max. There is a local max right there. There's a local max of 3 that occurs at 4, 3. Okay, is there a local min? No, it's not including that. See how it's open? No local min. And notice it keeps going down, so there's no absolute min either. Okay, so hopefully that helps on those. Now, extreme value theorem is just saying, hey, if you've got this continuous function meaning no holes, jumps, gaps, so if you draw it, you'll never lift your pencil, okay? Well, if you have a continuous function on any closed interval from A, we'll put it from A up to a B, then you're guaranteed that you're going to have an absolute max and min on there somewhere, right? So in this case, this would be our absolute min, and since it goes up to here, this would be our absolute max since I'm going up to a B value, so right up there. Whoops. Okay, so you're guaranteed if it's a continuous function from A to B, you'll have one. Average rate of change. This may look familiar, this average rate of change. All this is a slope. So when you hear average rate of change, just think slope. All this is y2 minus y1 over x2 minus x1, just in a different form as they're given. Instead of giving it to you with x1, y1, x2, y2, they're giving it to you in terms of a, f of a, and a b, f of b. Okay, so this average rate of change, this will be very handy as you progress in your mathematics careers here. Let me give you an example. Find the average rate of change. So all you're thinking is find the slope. Find the slope. Okay, and let's do it for this first one here, from 1 to 3. So you've got this function 3x squared, and you're doing it from 1 up to 3, right? You're doing it from 1 to 3. So you're just finding the slope from 1 to 3. What is the slope of that secant line from 1 to 3? That's what you're doing. So we have the two x's. They're giving us from 1 to 3. So you got to find the y's. So what's the y? Well, you plug the 1 in. So you got y equals 3x squared. Plug the 1 in. And you've got 3. So 1, 3. Now plug the 3 in. It looks like you got 9 times 3, you got 27. 27. Okay. Now you've got your x1, y1, x2, y2 to then run your slope. Okay. In other words, f of b minus f of a over b minus a. Same thing. Okay. So 27 minus 3 over 3 minus 1, 24 over 2, looks like we got our 12. So the average rate of change is 12. And so here's a little bit better picture of that. That's saying, you see this red line right there? That's saying the slope of that red line is 12. The average rate of change is 12. Even though this function is more, it's more dynamic than that. You see, you got curvature to this. We're just averaging the rate of change. So what's the slope of that secant line? All right, thanks for watching. See you guys in class.